Okay, salam sejahtera and good afternoon, guys. Today we will talk a little bit on the topics regarding corrosion, right? So for the learning outcome, at the end of the course, you should be able to understand some of the mechanisms of the corrosions of reinforcements. And then basically in the corrosions, there are two factors. One is from the chlorides and also another one is from carbonation, which we are also going to discuss later on. And then the factors that influence the corrosions and some of the methods for rectification. All right, so for the backgrounds of the corrosions, it is actually commonly defined as a deterioration of substances, usually a metal, or to be exact, is a ferrous metal, or its property because of the reaction with its environment, for example, like the oxygens and also with the moisture. And then like any other natural hazards, corrosion can cause dangerous and expensive damage to everything, such as automobiles, and then we have home appliances. This is your washing machines, and then the drinking water systems, your pipes, pipelines, bridges, steel bridges, and also some public buildings. And then the impacts of the corrosions can be very big. For example, it will affect our national treasure, economics, environment, our safety and health, and also national security. So if according to the NSC 2016, so approximately 451.3 billion US dollar was used for the corrosion costs only in 2016 alone, and it is about 2.7% of the GDP of USA. Meanwhile, in Malaysia, the corrosion cost is about 6.7 billion USD, and it is about 3.23% of GDP. As you can see, the impact of the corrosion in terms of the economy. So actually, the corrosion, there are lots of types. You have the uniforms, like this one, and then you have pitting, where you have hole in the metals or in the steel, and then you have the crevice, and then you have the galvanics, erosions, corrosions, intergranular, and so on and so forth. And the types of corrosions are basically there are a lot. Okay, and then what we are going to discuss today actually is the deteriorations or the corrosions of reinforcement when it is inside the concrete. So most of us have believed that when we put the rebar or steel reinforcement inside a very hard concrete, so basically it won't become corroded. Okay, but actually that is only a myth, right? Because the performance of a reinforced concrete, if you look at this picture, yeah, it will decrease. Okay, it will decrease with the increase of the time. Okay, so the longer the time, the performance of the structures will deteriorate, because of the corrosions of the steel bar, and it needs periodically maintenance in order to put it back. Okay, in order to improve its performance and to maintain its performance. Okay, so for the protections of the steel in the concrete, while in the normal situation, so steel normally is passivated due to the alkalinity of the concrete. As what we have already discussed in our previous class, the pH in the concrete actually is more than 12.5. When the pH of the concrete is more than 12.5, so basically the steel is being protected by a passive film. Okay, and then this passive film actually is a microscopic oxide layer formed at the steel surface. Okay, and this oxide layer will impede the dissolutions of iron. So what actually is the dissolutions of iron? We will discuss about this later on, right? Okay, and then the corrosions of the reinforcement, it does impossible. Okay, and then what actually is the passivity or the oxide films, as it will occur when the pH level is high, which is normally more than 12.5, right, leading to the formations of the passive layer, and then the chemical binding of chlorides, and then dense, it happens under the requirement that it is dense and impermeable structures of concrete, and this is the conditions for the passivity. Okay, where your steel is how to say, is being protected against corrosions. Meanwhile, depassivations is the opposite of the passivity, where your steel is has having the has the tendency to be corroded. So it can be happen due to the ingress of the chlorides or the chloride ions to be exact, and also the carbonations of the concrete. So the factors influencing the corrosions of reinforcements, we have chlorides. It must sometimes of the chlorides. Chloride is acid. It will neutralize the alkalinity in the concrete, and then we have carbonations. Okay, carbonations, and then moisture, and then it must happen concurrently with the existence of the moisture and also with the oxygens, and then some other factors, for example, like concrete mix variable. Okay, some concrete mix variable, for example, when we are using the chloride base of the set accelerators. Okay, and then the construction variables, for example, like the concrete cover, and then temperature and also humidity. Okay, so some of the mechanisms of corrosions, and also the corrosion protection. The process and the effects: passive films may be destroyed locally or over greater surface area due to the carbonations or by chloride ions. So this is what we call as micro cell corrosions, and this is what we call as macro cell corrosion, right? And it can be because of the micro cell and also macro cell, yeah, or due to both. And then the third mechanism is the reductions of alkalinity due to the leaching out of alkalis by streaming water. Okay, so how does this streaming water or the leaching out of the alkalis can happen in the concrete? So in practice, this may happen in the regions of the weak joints of the structure. For example, like at the leaky construction joints and at the wet cracks, or in the combinations with bad concrete qualities. For example, like when your concrete have a big gravel pockets or very high water cement ratio, which resulted in a lot of air voids. Okay, so what about the carbonations? So this is the mechanisms of carbonations where the carbon dioxide, yeah, they react with water, yeah, to f- to form the carbonic acid, right? The carbonic acid, and then it will interact with this calcium hydroxide, in order to form calcium carbonate and also water. Okay, so the carbonation actually is a reaction between the acidic gases in the atmosphere and the products of the cement hydrations. Okay, so this is normally when you have a steel inside your RC, inside the concrete like this. This is what we call as reinforced concrete. So the exposed surface, it is carbonated, because of the carbon dioxide in our atmosphere. And then over the time, after maybe 10 years, 20 years, right, the carbonation, it will go into our concrete. So if the carbonation zone is not reaching your steel bar, then the corrosions won't happen. But if, like in this case, after the carbonation zone has already reached your steel bar locations, this is when the corrosions of the reinforcement bar will happen. So the carbon dioxide diffuse the concrete and react with the calcium hydroxide, and it will reduce the pH level. Okay, like what we have already discussed earlier, when the pH level of the concrete is low, the passive films of the steel bar will be gone. Okay, and then this is carbonations of the concrete. The carbon dioxide may penetrate and react with the calcium hydroxide, and the chemical reactions may be described as the carbon dioxide plus water, and it will form the carbonic acid. And then the calcium hydroxide plus the carbonic acid will form the calcium carbonate. Okay, and it will drop the pH in our concrete. So the reinforcement corrode, if sufficient moisture and oxygen are available. So these are the two requirements. So in order for the corrosion to happen, and so aside from the like the chloride and also the carbonations, moisture and oxygen must available. Okay, so the carbonation is the process by which the carbon dioxide from the atmosphere slowly transforms the calcium hydroxide into calcium carbonate in the concrete. And the concrete itself is not harmed and increases in strength. Yeah? But the reinforcement can seriously affected by corrosion as a result of the process. So the concrete will not harm, which means the properties of the concrete, for example, like strength and the durability, will not harm, and increases in strength, okay, a little bit. But the reinforcement will be seriously affected by the corrosion. So normally, the high pH level of the concrete prevents the corrosions of the reinforcing bar by keeping them in a very highly alkaline environment due to the release of calcium hydroxide by the cement during its hydration. So this is the Portlandite, and then the carbonated concrete has a value, which has a value of pH level uh, 8.3, while the passivations of the steel start at the pH value of 9.5, and the depth of carbonation in good dense concrete is about 3 mm. At an early stage, it's about 3 mm, and may increase to 6 to 10 mm. Okay, 6 to 10 mm after 30 to 40 years. Okay, so it takes a very long time to happen, and but in poor concrete, right? The depth of carbonations of 50 mm after 6 to 8 years can be formed. Okay, so the rate of carbonation actually depends on the time, and the times, and then concrete cover, your concrete cover, how deep is your concrete cover, concrete density, your cement content, your water to cement ratio, and also the presence of the crack. So the carbonations of the concrete can be controlled, right? Can be controlled if our concrete structure is being maintained. Okay, and this is the rate determining the process of the diffusions of carbon dioxide into the concrete, which follow the square root time law, right? So if you look at here, so this is the square root time law. So we can see that, yeah, the rate of carbonations, which is the increase of the carbonation depth with the time, the ultimate value decreases, yeah, decreases with the decrease of the permeability of the concrete and the amount of the carbonizable substances, okay, and increasing environmental humidity. Okay, so the concrete quality parameters in relation to carbonation is actually the permeability. So it will affect, yeah, how what we call the diffusions of the carbon dioxide. Okay, the diffusions of the carbon, or to be exact, the rate of the diffusions of the carbon dioxide. And the diffusions of the carbon dioxide is only possible in air-filled pores. All right. So theoretically, for a totally water-saturated concrete, okay, because the diffusions of the carbon dioxide cannot be happened, yeah, because the air pore is already saturated with water, so the carbonations will not happen, right? Theoretically. So beside the carbon dioxide, chloride ion, which is originating from the seawater and also the icing salts, yeah, this is types of a chemical, okay, may penetrate into the concrete. So these are the sources of the chloride ion. And then the chloride intrusion is due to either diffusions or capillary functions. So this what is diffusions and also capillary function is can be found in our topic, which is in the transportation, yeah, in the transportation mechanism. Okay, transportation mechanism. And then however there are times where the chloride absorbs in the concrete in the form of contaminated material, for example like seepage aggregates and also admixtures. Okay, some of the admixture, for example like the set accelerators, okay, are chloride based, okay, are chloride based. And then as a result of the diffusion process, the concentration will decrease from the surface to the interior of the concrete. So to a rough approximations, okay, it again follow the square root times law, where you have the square root times over here. Okay, square root times law. And then due to the wetting and drying of the concrete surface with chloride containing water, an enrichment of the chloride in the surface layer is possible. So due to the wetting and drying, the chloride contents will accumulate in your concrete. And then the water penetrations and also the permeability of the surface layer are important. And then it is in relation with the thickness of the concrete cover. So if you want to increase the durability of your, for example, like the RC, so this is the reason why we have to thicken our concrete cover, right? And then this is the de-icing salt. Okay, de-icing salt is normally used, de-icing salt is, which is normally used to melt the ice. Okay, used to melt the ice. Okay, so this is the mechanism of the corrosions of reinforcement. So this is the typical. So in during the corrosions, we have the analytic process. Okay, we have the analytic process, and also we have the catalytic process. Okay, so in the analytic process, which is normally what we call as the dissolutions of iron, is the ferrous. It will reduce to ferrous plus and also two electrons, which is in negative charge, and in the catalytic process, where we call it is a consumption of the electron, with the existence of the oxygens and also water or moisture plus the electrons, it will form the hydroxides. Okay, it will form the hydroxides which is in negative charge. So the ferrous plus the hydroxide, it will form ferrous hydroxide. Okay, so under the high concentrations of the chlorines ion, it will cause the corrosions of the reinforcement, and the products of corrosions can disrupt the concrete. And corrosion can be introduced into concrete either during or after construction. For example, when during the construction, chloride is admitted into concrete through the admixtures containing the chloride, calcium chloride. Okay, and then also through the mixing water, which is contaminated with the seawater or improper wash machine aggregate, marine aggregate, sorry. Okay, and that is before constructions and how the chlorides can be emitted, and then after the constructions, it can be due to the salt or seawater, and in airborne sea spray and from de-icing salts can attack the permeable concrete, all right, and cause the corrosions in the reinforcement. Okay, so cement actually they have certain chemical and physical binding capacity for chloride ions, and then they will form the Freda salts. Okay, depending on the chloride concentrations in the pore water. But however, not all the chlorides can be bound. Okay, so if the chlorides cannot be bound, it will become the free chloride ions, as is in our pore water, and only the free chloride ions are relevant to the corrosions of the reinforcement. The free chloride ions is responsible for the corrosions of the reinforcement, and it is important to know that after the carbonations of the concrete, bound chlorides are released again. Okay, so that the chlorides content in the pore waters are consequently the risk of the corrosions due to chlorides will increase considerably. So these are the examples of the corrosions due to the chlorides, and the steel has been severely being corroded, and also like the bridge pier, you can see the reinforcement inside the bridge has already been corroded. Okay, and then the corrosion process can actually, like what we have already discussed earlier, be separated as a catalytic and also the analytic process. Okay, this we have already discussed earlier. Okay, and then because of the corrosion, the steel bar, steel rebar will become rusting. Okay, and the rust will expand. Okay, rust will expand, and it will cracks our concrete, as you can see in the schematic diagrams. So like what we have already discussed earlier, at the analytic process, we call it as the dissolutions of the iron, where the iron, which is the ferrous, okay, positively charged ions pass into solutions. Yeah? Okay, this is the formula. And then at the cathodic process, where we call it is the consumptions of the hydroxide, is the surplus electrons in the steel will combine at the cathode with water and oxygen to form hydroxide or iron. Okay, to form the hydroxide ions. So that is the formula. Okay, and then the iron and the hydroxide ions will combine to form rust. Okay, which can be written as the ferrous oxide. Okay, which can be as a ferrous oxide. So only oxygen will be consumed to form the iron oxide, because it is ferrous oxide. So only oxygens will be consumed, and the water is necessary, yeah, because it will enable the electrolytic process to take place. Yeah, the electrolytic. So without water, okay, the rusting will not happen and corrosions will not happen. And then we might also bear in our mind that the corrosion will not occur in either two of these conditions. In the first one is in very dry concrete where the electrolyte process is impeded, and in water saturated concrete where the oxygen cannot penetrate. Okay, and in the anodic areas, the passive film must be destroyed. Okay, whilst in the cathodic areas, it can take place even if the passive layer is intact. So that is the difference between the anodic process and also the cathodic process. So in the case of the chloride corrosions, and so this effect causes the pitting corrosions where the chlorides will act as a catalyst, okay, and it will accelerate the dissolutions of the ions. Okay, so this is chlorides, and it will resulted in the pitting uh, corrosion. And at the steel surface, anodically and cathodically acting area may be situated either close together, and this happens, we call this as a microcell corrosions, and it can be locally separated places or even over relatively great distance. This is what we call as macro cell corrosion. And corrosions may occur if the concrete is wet enough to render electrolytical connection possible. Okay, so now we are continue discussing the failure which can be due to the corrosions. And the first one is the stress corrosions, and the second one is the hydrogen embrittlements. So both of these failure are brittle in nature, okay, and they may occur in the pre-stressing steel. So very localized anodic processes may lead to the cracking due to the high permanent stress if the stress is sensitive to this type of failure. So during the crack propagations, the anodic process takes place at the root of the crack, as you can see here, and this type of the brittle cracking is called stress corrosion cracking, SEC, where the anodic reactions happen at the root here. Okay, so the second type of the brittle failure is the consequence of the cathodic process. So under certain conditions, the atomic hydrogen is developed, okay, during the cathodic process as an intermediate product and may penetrate into the steel. So if you look at here, the dislocations of H to become H2, which leads to the high pressure and the crack initiation. So this is what we call as hydrogen embrittlement. So both types of the failure are consequences of at least local depassivations, where the passive films of the steel has been destroyed and will not occur if the processing steel is totally surrounded by sound and hardened concrete or cement grout. So as a special case, the atomic hydrogen may develop at zinc-coated metal surface in the fresh concrete or either the grout. So, however, for two reasons, this risk is only temporary. The first one is the evolutions of the hydrogen will come to a stop when the concrete or the grout has hardened well. Okay, so this is the key point when the concrete has hardened well, and if the hydrogen penetrates into the steel without causing a failure, it will diffuse again, thus relieving the local bursting pressure and reducing the risk. So the influence of the cracks. So in the regions of the cracks, carbonations and chlorides tend to penetrate faster towards the reinforcement. Okay, so where you have crack in your concrete, and no matter how small it is our responsibility as an engineer to seal the crack so that the carbonations and chlorides will not ingress or penetrate towards the reinforcements. And in the case of the normal crack of up to 0.4 mm, self-healing as a result of calcium, dirt, and the rust deposits. So this is what we call self-healing process. And in this case, any ongoing corrosions at the reinforcement is likely to come to halt. Okay, and the carbon dioxide and also chlorides may penetrate into the steel through cracks. So the durations of the perforations depends on the crack width. So if you look at here, they show the relationship between the perforations time and also the crack width. You can see that with the increase of the crack width, the time to depositions will become shorter. And then in the case of a post-tension structure, durable preservations of the processing steel can be assumed if the first one is the cover of the ducts exceeds 50 millimeter and the crack widths are less than 0.2 mm at the concrete surface, and ducts are thoroughly and completely grouted and chlorides are absent. And here are four of the conditions where the steel has less tendency to become corroded. And then the corrosion processes in the regions of cracks. Corrosion's current measurements show that normally microcell corrosions occurs. The steel in the cracks region acting analytically while the kinetic processes take place in the uncracked areas beside the cracks. So this is what happened. In and then the influence of the crack width of the corrosion rate at the reinforcement is relatively small, and then substantially greater importance is the thickness of cover. So in order to ensure a more durable structure, so thicker power is required, and then cracks oriented transfers to the reinforcement are less harmful to the longitudinal cracks. Effects of the corrosion, so we can see that during the corrosion, rust will happen, rust will form. And when the rust is forming, so basically the volume is expanded. Okay, and that is why some of the phenomenon, which is what we call concrete spalling or concrete disintegrating actually come from the rusting of the steel. And then the corrosion process may result in the reductions of cross sections in the reinforcement and splitting of the concrete cover. Okay, and then the load bearing capacity of the steel will also decrease. And then the elongation properties and fatigue strength may be reduced due to the corrosions. And the latter two properties, which is the load bearing capacity of the steel and elongation properties, are more sensitive to corrosions. The elongation properties and the fatigue strengths, these two properties. And then, like what we have already discussed earlier, the rust has more than 6 times in terms of the volume compared to the steel. And then this leads to the splitting forces that may cause cracking and also the spalling because they push the concrete upwards, and the effects of the corrosions of reinforcement may lead to the sudden failure. So when corrosion develops in an environment with low availability of oxygens, the volume of the rust products may be around 50 to 200% greater than the volume of the steel. So such corrosion processes proceed very slow. Okay, and in special cases, the rust products may diffuse into the voids and pores of the porous concrete without causing cracking and also spalling. Okay, because the process is very slow, and then the corrosion may develop on the reinforcement without any visible warning, and suddenly it fails. Okay, so some of the influencing parameters to the corrosions of the steel, all the processes influencing the corrosions of the reinforcement are more or less controlled by the transport processes or the transport mechanism. So, like for example, the carbonations, which is the diffusions of the carbon dioxide in the air-filled pores, and then the second one is the penetrations of chloride through diffusions, and also capillary suctions of the chloride containing water into the air-filled pores. And the last one is the corrosions of the reinforcement, which is based on diffusions, right? Diffusions of oxygens into our concrete. So the major parameters in connection with the corrosion and also the protections of reinforcement in both uncracked and cracked concrete is the quality of the concrete cover. So this quality is defined as the term of the thickness of the permeability of the concrete cover. And another important parameter is the microclimate at the concrete surface. Yeah, microclimate. And the thickness of the concrete cover, how does this factor influence the rate of corrosions? Is the the carbonations and chlorides that penetrate to the interior of the concrete at a lower rate that would be given by the square root time function. And means that if the concrete cover is half, the critical state for the incipient danger of the corrosions will be reached in less than quarter of the time, right? So it can reach our steel in a shorter time. Okay, and then what about the permeability of the concrete cover? So it influenced by WC ratio, which is the water cement ratio, and the water cement ratio of concrete influences the permeability. So as a rule of thumb, if our WC ratio or water cement ratio exceeds 0.6, the permeability will increase considerably due to the increase in the capillary porosity. Okay, so this is the figure showing the volume of capillaries pores increase in terms of percentage, and the water permeability also increase significantly. All right, and the factor which is influence of curing is if the concrete is insufficiently cured, the permeability of the concrete surface may be increased by 5 to 10 fold. So curing measure must begin immediately after concreting, not be interrupted. And then curing sensitivity increases with increasing WC ratio and decreasing cement content. And then compaction, poor compactions will also tends to increase the permeability of the concrete, right, which leads to the corrosions of the cement. Corrosions of the steel. And then cement types. Okay, so generally the most common composite and blended cement is natural pozzolanous, blast furnace or fly ash, for example, have in common the properties of slowing hardening at an early age and also distinct hardening later on. And this means that composite and also blended cements are more curing sensitive than Portland cement. They need more proper curing methods. Okay, but with adequate curing, a lower permeability of concrete can be achieved. And then environment, so in permanently dry environments, the corrosion risk actually is very low. And even if the concrete is carbonated, and because of the electrolytic process impeded, so the corrosion actually can be prevented. And in the case of the high chloride content, corrosions may be possible even in a high environments due to the hygroscopic effects. We have already talked about hygroscopic when we talk about the timber, timber topic before this. Yeah, and then the major importance of the quality of the outer concrete layer, for example, the cover are due to the WC ratio, which is the water cement ratio, compactions, and last one is the curing. And the cement content mainly influences the workability, indirectly the permeability and the curing sensitivity of the concrete cover. So I think that would be all for this topic. Okay, I'll see you again in our next topic. So thank you very much and see you again.